And I have been studying, I suppose I've been in statistics for about 20 years, and more recently learned it's supposed to be called machine learning now. So in the last 18 months, I've been sort of doing more machine learning, and increasingly focused on the question of packaging and distribution, and really on the mobile side, how to get more sophisticated models running on the edge. And this is me presenting at a conference called Chain React, where I talked to 500 mobile developers about bringing on the edge ML, really DL technologies called TFLite and CoreML that they could then apply directly on their phones without having to make server calls. And we'll actually be talking about those technologies a little bit in a minute. But as I've been studying more of this, I've sort of found that there is this field that doesn't seem to be as much explored that I want to talk about more today, which is the idea of the code as data, right? And the question of models and how we transport them across platforms. There's sort of this old, Scala-ish idea of being able to represent code as data. It's core to metaprogramming, which is actually important to the way a lot of machine learning systems work. But the relationship between the code and the data is what I'd like to explore a little more today. By somewhat rapidly going through 5 different machine learning frameworks, 3 of which that involve both training and inference, and the last 2, TensorFlow and CoreML, that are inference only, and talk about what maybe the way they treat data tells us about these systems, and maybe what tells us about where this field might be going. So let's start with the one that's least like the others, which is PyTorch, which is really Facebook's entry in the machine learning space. And the really cool thing about PyTorch is you can just code. You can just write imperative code, and it will differentiate at runtime in order to do your training processes. And that's really fantastic. One, is easy to get started with. But second, it's actually the most Python-y of the systems because it's not dependent on eventually going into a C runtime to make it work properly. You get to make use of the dynamism that's intrinsic to Python itself. This gets reflected in the way that it treats data. If you want to serialize a model or information on a model from PyTorch, you use a serialization subsystem in the name. And that serialization subsystem is actually a relatively thin wrapper around Pickle, which is the introspection-based data serialization system for Python. Now, for those of you who haven't worked with this kind of system before, there's parallels in PHP and Ruby. It's kind of intrinsic to the way a lot of interpreted and more dynamic languages work, where essentially what happens is you say, I have an object, and I want to serialize it. And what it will do is say, oh, well, that object is a class of X. I'm going to go find all the properties of X. And all those properties are primitives. I'm just going to serialize straight out. This symbol goes with this primitive. Oh, wait, that's a pointer? Well, what class does that pointer go with? And down and down and down the tree we go. And then you wind up with a representation of the state of that particular object at that point in time. And you can see how that which is generalized to objects in Python also applies to most of our models. This is both incredibly easy to use. You don't have to do any setup to get this. It comes for free. It is core to the way Python works. It's also very limited. If you were to look at a Pickle file, at a serialized representation, you learn nothing. Because everything is dependent on the symbols that come from the original representation of Python. So it actually also creates a bit of a time travel problem. If you have a version of the code that serializes a model or representation, and then you change the code and then you try to deserialize again, ain't gonna work. And it can actually break in some fairly substantial ways. Now, as a matter of best practices, the good folks at PyTorch say don't do that, right? But also they say don't serialize your whole model, right? The best practice is actually to serialize not your model, but just the data dictionaries, right? Just the weights, to try to isolate yourself as much as possible from changes in the code that might otherwise be kind of trivial. But the truth is, if you make more significant changes to the code that changes your relationship with those weights, it's going to break. And in general, I would say that the key thing about PyTorch is that it's very dynamic, it's very easy to get started with, and it's very local. It does not lend itself to being able to transport its insights across platforms without significant additional work, which isn't impossible, but sort of takes away the PyTorchiness of it. And to illustrate what that really means. Let's look at like this polar opposite. That's probably Keras. Keras is totally metaprogramming, right? You are expressing, it's probably most well known for what's called a sequential API, which is this cafe-like structure of being able to say this layer goes after this layer, after this layer, after this layer, after this layer, which is really useful for a lot of machine vision applications. It was originally built to be a front end for Theano, and I don't know if anybody here has worked with Theano, but it really needed a front end. Of course, Theano has now largely gone the way of all things, and since Francois Chalet moved over to Google, it's mostly used as a front end for TensorFlow. But the UI is much like what it was, where the sequential API is very much what the classic is. There's additional functional API that allows you to make more of a DAG pretty easily. But one way or the other, it's all about metaprogramming. It's all about being able to describe the graph of operations and the weights that go along with that graph. And using the idea that in the main, you're working off a fairly limited set of operations. The really question is arranging them, and of course having the weights trained. So the way this information gets stored by Keras uses basically two formats. One is JSON for expressing the graph, and the other is what's called HDF for expressing the weights. We'll talk about each in turn. On the JSON side, I think this is great. Because the way it expresses a model, and this is a classic sequential model from Keras, is readable and inspectable by a human being without requiring being in the context of Keras, right? You can infer, oh yeah, this is a convolutional error, because I can tell because it says con in 2D. I can figure out how many filters it has. I can understand its kernel size, right? It lends itself to understanding just by looking at it, rather than having to load in context. The complete opposite of what we're talking about with PyTorch, right? It's not dependent on the symbols at runtime. It's basically compile time and aliased in a way that we can get. And you can look through this, and because we're looking at the graph of operations, even when it has hundreds of operations, you only talk about a couple thousand lines, it's actually relatively easy to understand, especially if you use a tool like Prettier, which I just did, in order to make it lay out more easily, so I'm not trying to understand all the details of what's nested inside of what. Tabbing takes care of that. On the weights side, it uses a system called HDF, which originally came out of University of Illinois. In fact, the same group that birthed the web browser back in the early 90s. The idea behind HDF is that it's basically a tarball for high-dimensional numbers. So you can have an H5 file. It's on currently version 5. That's why they say H5. And each number that you have inside, right? Each layer, each set of kernels, what have you, is treated like a file that's inside the tarball. Has meta information that tells you what the shape is, and it's being stored usually based on a standard 4 by 32-bit notation, which means it is perfectly inspectable at a low level. And so you can actually use tools like HDFU, which actually comes out of the HDF group, which again comes out of University of Illinois. These are the people who invented HDFF. It is not the prettiest interface in the world, but you get to see the actual numbers. And I find that to be tremendously helpful, and see it actually in its original shape. And because the name of the file, like dense1 here, it actually ties to the name of the layer that's in the JSON. So you can just go back and forth and understand what else is going on. There's a second tool that you might want to check out called Panoply, which comes from basically the terrestrial information side of NASA. NASA uses H5 for the geographic information service that basically maps satellite data over maps so they can figure out what is happening. As a result, Panoply is much better if you want some cooler visualizations, but HDFU is still my go-to when it comes to actually looking at the data. Both of these are jars, so they're completely cross-platform. Now, we talked about the JSON. That's great for the graph. We talked about the H5, and that's great for storing the weights. But if we want to talk about portability, we want both of these to go across at the same time. And of course, they are two different formats. So what Keras does is it does a little cheat. You see, that meta information we saw about like the shape of the number, well, that also applies to the very top of the tarball of the H5. And you can have meta information, basically key value pairs that get stored at the top, which are ordinarily for little text, like, hey, this is going to be, like a 10, 12 digit or character values. But Keras realized, in fact, there is no upper limit on the size of a lot of these meta values. And as a result, in addition to being able to say, yeah, this is eventually going to be for TensorFlow and was built by Keras 208, here's the whole graph. And that means we have in one file everything we need to know about the graph of operations and its weights for reproduction outside of the original runtime. It is inspectable by a human being. It is understandable, basically, without having to load it all into the matrix. And I find this to be kind of gold standard for human inspectable meta programming. But that's not what most people use. TensorFlow, probably the single most popular of the deep learning frameworks. Instead, it has two modes of operation, right? It has one that's called eager execution. And eager execution is sort of the PyTorch-like way of using it, where you can just express what you want to do and it's being interpreted inside the Python runtime. It has a second mode of operation that's actually more popular called Graph API, which is basically metaprogramming that is saying, I'm going to express what the DAG is of the model that's supposed to run, and then that DAG actually gets shipped to a C runtime that's outside of Python for the purpose of differentiation and evaluation. Now, there's also sort of a cool new thing over at Google too, which is called an autograph API that allows you to code as if you're in eager execution mode, but actually create a graph so it can actually ship better. But that's not really the scope of this conversation. Leave aside the eager execution, because that's not metaprogramming. Let's focus instead on the graph API, which is actually portable. And the way that graph gets stored is, in the main, a protocol buffer. Now, the protocol buffer is technology that Google came up with about 12 years ago that allows you to basically relatively efficiently transmit complex, structured information over the wire. So you might have this big object that's made up of other objects, et cetera, et cetera, et cetera. And the idea is we want to transmit a minimum number of bytes over the wire without using compression. We want to have a minimum memory profile at either the encoding or decoding end, because the main use case here is actually for microservices, where you're going to have lots of instances and you don't want them to be having to consume a lot of memory. As a result, you don't want a document object model where everything has to be loaded to memory at once. You want a streamable model. For that, you need a schema. So the key to a protocol buffer is going to be defining a schema that says this is the structure of the information we're expecting, which includes, by the way, sort of a classing so that one object can store another. Of course, it's all data only, so it's structs, not objects. And then one of the cool things about it is, after you define that schema, it is actually deterministic between the schema and the code that would be necessary for doing either the encoding or the decoding. And so there are protocol buffer compilers that will take any given protobuf schema and turn it into Swift code, turn it into C code, turn it into Java code, so it can just run with a minimum of memory in that environment. And basically, so now your schema gets compiled into your code base for maximum performance. Okay, that's cool. We're trying to go for high performance. That's nice. And it all stays very, very small, because as long as you have a schema, sorry about the blurriness, as long as you have the schema set up, then unlike with JSON, where you keep on repeating your keys and your keys and your keys, you can just have these aliases that are basically numbers. As long as those numbers are known by both sides, that structure can stay very terse. And that is what they value. They value having a low memory profile at the point of serialization, deserialization. They value being terse over the wire and also in the file. And they also value reliability, right? So they're all working on the same schema. Okay. So in order for this to be valuable, you need to know where to find that schema. If you ever want to go unpack that yourself outside of core TensorFlow, and you can. It is actually all on their GitHub repository. And I'd actually encourage you to go look at it, because if you look inside one of these protocol buffer schemas, you'll find they're actually pretty easy to read. And for me, at least, it gives a lot of insight as to how TensorFlow thinks about its data to have this information all up here. So That's the schema side. Let's talk about that terse representation I was just talking about, which if you're working with TensorFlow, it's usually called a graph-def file. The graph-def is going to contain in its core just all these little numbers that reference the various messages. It's going to have your data. And if you want to just look at it without the benefit of a schema, you can. And I like to use Protobuf Viewer from the Mac App Store for this job. It doesn't require any additional work. I can take any graph-def or any other thing that actually is stored as a protocol buffer, load it into memory. And in fact, I find that because machine learning models in the main actually aren't that complex code-wise, the structure of the data, I can often get a lot from context and be able to read it about halfway. Now, there's a second thing that's called Protobuf Editor, and actually there are half a dozen tools that will do this, that will allow you to point to a schema, i.e. a proto file, also point to your, say, your graph-def, and then it will put them together, so instead of having the numbers over here, you have the labels. It takes a little bit more setup to do, but if you're not as comfortable with what you're seeing, it can be helpful. But before I leave TensorFlow, I'd like to just dive in for a second to this representation here. These are weights. You see, protocol buffer was designed to solve the problem of transmitting complex, structured data. You know what's not a complex, structured data? A data frame. And weights are data frames. So that high dimensional number that was all being set up with meta information, what have you, that we have for an H5, yeah, it looked like this. And I find this to be exceedingly unhelpful. I can't read the weights without having to look, without some non-trivial work of loading it into a runtime to be able to understand it, at which point I might as well be using TensorBoard or something. So what I find this tells me about TensorFlow is that TensorFlow is putting a primacy on the graph over the weights, right? It's about being able to handle this structure with a good degree of terseness, of sophistication, but the way it actually handles the weights, which actually is the vast majority of the file, bytes-wise, is actually kind of dumb. Okay, I hope I didn't offend any Google people. But don't worry, I'll talk about Google again. Here's TensorFLite. TensorFLite, now we're going from things where you can do training to things that are inference only. Nobody builds a TensorFLite file. You convert from something else to it. TensorFLite is really designed with Android in mind, and a Google person will argue with me that in fact it runs on like Raspberry Pis and iOS as well. This is true, but its design considerations are really Android design considerations, and this gets reflected in the way that it treats its data. You see, a TensorFLite is going to interpret data using something like this protocol buffer, but not quite. They create something called a flat buff. And a flat buff is solving sort of the problems that you face when you're on Android. And on Android, you face three problems at the same time. One, you've got limited access to network. You want things to be really, really terse. Actually, you kind of get that with protocol buffers. And there's also first class in the TensorFLite implementation protocol buffers for quantization, i.e. storing these numbers not as 4-byte 32-bit, 4-byte floating points, but being able to reduce them to 2-byte or 1-byte specifications. The second is that it will, second constraint is as a limited access to memory. So we need to stream it in a way that doesn't have to load as much into memory. And this is actually a problem related to protocol buffers, because while I talk about protocol buffers not needing that much memory to stream from the original into the destination, an assumption of protocol buffer is you're streaming from the original into the destination. You have the destination in heap. And if you have limited memory, you don't want that. And the third consideration is have very limited disk space. That, like, if you're dealing with quote, quote, internal storage on Android, you need to be very lightweight in the way that you touch it. Even though you might jam in an additional micro SD card later, you don't actually have access to that usually at runtime when you're dealing with cache. So that means that they don't want to have to load this whole thing into memory, and they want to be terse. And they can't use a caching approach to sort of break it up as they're interpreting. So how do you do that? And this is where flat buffers come in. Flat buffers are a variant on the protocol buffer, where the design principle is that instead of recursing through the objects nearly so much, they're defined at top level, which means they can be indexed. And that means that instead of having to say, well, here's my whole model, I'm going to do sequential access through the file to bring it all to memory, I can have random access and say, well, now I actually just need the weights for this particular layer, so I can go map that into memory in order to get run by my GPU, and then the next thing, and the next thing, and the next thing. Well, that's what flat buffers really affords. And that's going to be the key difference between a flat buff and a protocol buffer. Does that make sense? I know that was a little... So again, the flat buff specification is available on Google's website. They call it an FBS for flat buff schema as opposed to a proto file. I don't know why they gave up proto, but whatever. The other thing I would just quickly note is that it has much more built-in support to the point where it has turned the definition of operations into an enum instead of just like a string typing, which means it's not that extensible. Now, there is such a thing as a lambda layer, which you can use whatever you want in. But in the main, it's designed to start with a list, I think, of about 50 operations. And in fact, you can even decide to only compile in support for like 20 if you think that's all you're going to use. This might be significant, for example, if your sole use case is going to be machine vision, right? Then you don't need to compile in the RNN support. Okay, 4 down, 1 to go. CoreML. CoreML is Apple's entry into inference-only machine learning, and really heavily into the deep learning aspect, because really the big use case for both TensorFlow-Lite and for CoreML is to be making sense of sensory information, audio, text, a video that's coming in the door, because that's what you have on your phones. So it actually uses protocol buffers. It doesn't use something as fancy as the flat buff. It just goes for core protocol buffer specification, which is all available on this website that Apple runs. And if you look inside this, you will find that it has all the things you might expect, right, in terms of definitions for feature type, for how operations run, et cetera. And a lot of these look the same way they do in TensorFlow because they're smart enough to know that's where one of these things are coming from. But it has support for something else too. It has support for first-class feature engineering in the protocol buffer. So to go deeper a little bit into this, what does that mean? Usually, when we think about what's going to be inside the model, the part that's actually being shipped off to sea or whatever, we think of it starting with a high-dimensional number, right, like 300 by 300 by 3, something like that, where your values are all between 0 and 1 or whatever the value is. And then ending with, let's just say you're doing ImageNet model 1,000 by 1, right? Array of potential classifications. Well, what CoreML does is say, well, you can actually have a layer in front of that first one. Instead of saying 300 by 300 by 3, you can have an image. And by the way, we know, because we're in Apple land, that an image starts with certain parameters. We know that's going to be RGB, for example. And we can say things like, well, actually, my model is expecting things to be coming in VGR, which actually happens a lot because a lot of machine vision models are built downstream from OpenCV. And a lot of OpenCV work is, in fact, blue channel first as opposed to red channel first. There's another consideration. What about scaling? When I get a value that is from an image, right? I will get a value that's between 0 and 255, right? It's a byte for a given channel, for a given pixel. Well, here we might actually want that to be scaled to a value between, say, 0 and 1, or maybe -1 and 1, depending on how it is we build our model. And knowing that is actually important. That usually is something that we do in a pre-processing step if we're doing it server side. Like that's something we would do in Python as opposed to doing it in C. This makes sure that we put it into the protocol buffer. So instead of making it the developer's problem to know how this model works, the developer says, I just have an image. Get started. The same thing applies to the back end. Instead of having a 1,000 by 1, which is what your model would ordinarily do, and then you map it to like your new line delimited file of categories, just put your new line delimited definition inside the protocol buffer itself, add a layer at the end, and now you have a model that ends with basically a hash map, or as Swift calls it, a dictionary. And in 8 lines of code, a Swift developer who is consuming one of these models can go from downloading the model, running it through a compile step. By the way, this is how Apple solves that, those 3 constraints I was talking about on the Android side. It says we're going to basically shred an ML model and turn it from protobuf into a directory structure of all sorts of little cache files. We're going to feed it an image, we're going to predict the results, and we're going to pull out a dictionary of key value pairs, which are the labels and their scores. And then pull the first result and I get to move on. So I don't have to know anything about the sequence, I don't have to know anything about the order. As an application developer, all I care about is that there's a label coming out and I just need to have some sort of meaning associated with whatever that string is going to be. But that's a much lower level of cognitive load for an app developer than trying to say, okay, I have a number, what do I do with this? And I found that to be helpful as well. Now, this is all what you got with version 1 of CoreML. But just this past June, there was WWDC. And at WWDC, they introduced something called CreateML, which I thought was kind of interesting. CreateML is basically a demo for Swift Playgrounds that allows you to create an interactive image classifier, where you can just drag and drop folders full of images, and it will bring out and it will churn through your make your Mac very hot for about an hour, and bring out a model at the end, which of course classifies based on the names of the folders you put in, right? If you've ever used Lobe or some of those other services, it's basically the same thing, just local. But the file is only 20K. There is no machine vision model that's 20K that I can imagine. It's not like this game or something. In fact, not even those. So what's going on here? And I'm sure most of you who are familiar with transfer learning probably know the end of the story. But basically what's happening is it's a transfer learning model. And of course they're using a base model to then stacking a couple layers on top of it. And the cool thing is that in CoreML 2, they have added to their specification for the protocol buffer that instead of just having this feature engineering, it passes in a whole model by reference, which is now just defined one message, tiny. And that base model we're talking about is being deployed with the operating system. And this model by reference is then being used. It includes everything about like the feature engineering part in the front and taking me all the way to a bottleneck point. And then I'm going from bottleneck point, basically doing pooling, softmax done. And that, I thought, was pretty neat. And I think it kind of points where some of this could be going, because it tells us about how the job, right, of what we think of as being in the machine learning side can expand to be able to serve not just the question of being able to run some numbers, but be able to give us meaning, to have meaningful input that's useful from the application developer's point of view, an image, not a high-dimensional number. Meaning from the point of view of output, having a label, right? What is this? As opposed to just an array. And being able to make better reuse, right, of things that we might already know. And actually, Apple's also doing some interesting things on this on the NLU side around standardizing vectorization, as well as lemmatization, as well as first-round embedding, so that you can have similar kinds of results with both small data and small file sizes for being able to do things like sentiment analysis and tagging. But I think the big opportunity here is people like Gant Laborde. Gant Laborde, who I met at this GeneReact conference back this summer, he's a front-end person, and a very smart one. He's a senior consultant at a company called Infinite Red. If you're looking for good React Native work, they're good. And he took this idea of being able to relatively easily put ML tech into an app, and he wrote an app. It's like 300 lines long of JavaScript, most of which is having a good time to create a Nicolas Cage detector, combining face detection with image classification to create a sort of, an ersatz regional CNN object detector, basically, to find Nicolas Cage. Now, the amount of code he had to bring in order to link it with the machine learning part, it's like 12 lines out of this few hundred. He gets to focus on creating a really cool experience for the users because there's a better separation of concerns between what should be the basically these functions that we're writing that can be consumed by the app developers, and where his art gets to come play. And so I think with Gant in mind, I think about where we can be going and how we can be letting him think more outside the box by us giving more consideration to what we put in. Thanks so much.